But let's give this one a good look. Now here they say we have two charges, Q1 and Q2, having the magnitude of 4 and 3 microcoulombs. Okay, we are given the sign of this 4 microcoulomb, but we are not given the sign of the 3 microcoulombs. Okay, and then they say those charges have those magnitudes in that order. That's the meaning of respectively. And they say these charges are placed in a vacuum, as we can see in this diagram. P is a point at a distance r to the right of the charge Q1 and 0.2 meters to the left of the charge Q2. Now they say the net electric field at the point P is equal to 0. All right. So now they want to know, are the signs on the two charges similar or opposite? And give a reason for your answer. Well, for this one, you need to think about it. What happens if the signs are the same? And what happens if the signs are different? Okay. Well, I think we need to go to a free body diagram to show the electric fields that are acting on this positive test charge, which is Q. All right. But firstly, let's draw this sketch and see how it's supposed to look like. So here we understand that we have the charge Q1 and we also have the charge Q2 there, which are nice, by the way. And we also have a positive test charge that is between them, but of course, not exactly between them. So somewhere there, we are going to have a positive test charge, and that is fine. And we are given that the distance from here to there is r, it's unknown, and the distance from here to there is 0.2 meters. That's fine. And this is our positive test charge P. And this one is our Q2, which has an unknown sign, but the magnitude of the charge is 3 microcoulomb. And this one we are given Q1 having a magnitude of 4 microcoulomb, right? So now we go and say, okay, fine, this is our positive test charge. And we want to consider two situations. The first situation is when both of these spheres are positively charged, all right? So let's assume this one will be positively charged as well. Then what is going to happen to the electric field, the net electric field there? Let's see. Well, Q1 is positively charged, so it's going to repel P, okay? So Q1 is going to push P in this direction. And what about Q2? Well, Q2 is positively charged as well. So it's going to repel the positive test charge and it kicks it in the opposite direction. Okay, fine. But now what about if the sign of Q2 was negative? Yes. Well, if the sign of Q2 was negative, then the force, or rather the electric field of Q1 on P will still be the same. But what about this one? Well, Q2 is now going to pull this positive test charge towards itself as well. So we can get something like that one. And in the second scenario, we can see that the net electric field cannot be equal to 0. Do you see that? So I think before you can answer, try to draw for yourself a free body diagram and see what happens if Q2 is positive and also what happens if it is negative, and then give them the reason, all right? But here we'll tell them that Q2 is positively charged Yes, why is Q2 positively charged? Well, it's because in order for the net electric field to be equal to zero, what must happen? That's a very, very good question. Are the signs on the two charges similar or opposite? Yeah, the two charges. Oh, wait a minute. I think we are missing the point. No, no, we are not missing the point. Two charges Q1, this one and that one are placed. Okay. No, no, we are not missing a point. The electric field at point P is equal to zero. Okay. And then we said if we look at what is happening at P, how did I say the sign here is going to be in that direction? How did I come up with that? Hey, it's supposed to be positive, right? So positive and positive are going to repel each other. So meaning it's going that way. Okay, I was right for that one. That's fine. Now what about for Q2? Well, for Q2, if it's positive, then Q2 is going to kick P. Yes, yes, yes. No, we are right. So the signs on these two charges are going to be the same. But then what is the reason for those charges to be the same? And it has to do with the electric field. We need to answer in terms of the electric field. I think maybe we can say if those two charges are both positive, which is similar or the same, then it means the electric fields that they exert on the positive test charge P will be in opposite directions. Yes, I think if you said that, those two electric fields will be equal in magnitude but opposite in direction. Yeah, because I can't think of a formal reason why we can say, oh, why are we supposed to say those two charges are similar? Maybe I can quickly try to look for the memo so that I can see what they said. Okay, this is the answer from the memo. They say same sign. For the electric field at point P to be zero, the two electric fields must be in opposite directions. So that's what the memo is saying. It doesn't mention the magnitudes. It just says for the net electric field to be zero, that's if the two electric fields are in opposite directions. Okay. So that is the correct free body diagram for our situation here. Eish. Yeah, these things of reasoning. Guys, please be careful of that. Then the electric field pattern, we are not going to look at it. Then they say define the term electric field at a point. Well, we know that it's the electrostatic force that is experienced per unit positive charge placed at that point. Then lastly, they say calculate the distance r in meters. Okay. Okay. In order for us to find the distance r, we need to use the fact that the net electric field at P is equal to zero. But what is the meaning of the net electric field is equal to zero? It means the electric field that is exerted by Q1 on the positive test charge will be equal to the electric field exerted by Q2 on the positive test charge as well. Those electric fields are equal in magnitude but opposite in direction, okay? Then now you can come and say, but how do we calculate the electric field of Q1 on P? Well, of course, we say it's KQ1 divided by R squared, okay? But what about in the second one? Well, here you say it's KQ2, and this is divided by R squared as well. But now it's time to be specific. Well, K is 9 exponent 9, and Q1 is 4 microcoulomb, and R, well, the difference between Q1 and P is actually R, so there's not much we can say. Then we come back here and say 9 exponent 9, and it is multiplied by 3 microcoulombs. And then we say this entire thing, of course, is divided by the distance between P and Q2, which is given to us as 0.2. Okay. So now we can calculate the numerator of the first term and say 9 times 10 to the power 9 multiplied by 4 times 10 to the negative 6. And in the numerator here, we get 3.6 times 10 to the power 4. Simplify your workings, okay? And it is divided by R squared. Well, this one, we can actually find its value. We can just press everything into the calculator and get a single value. So we have 9 times 10 to the power 9 times 3 times 10 to the negative 6. And this is divided by 0.2 squared. So we get 6.75 times 10 to the power 5. And of course, this one, we understand that it has a denominator of 1. Why are we giving it a denominator of 1? Oh, it's because we want it to cross multiply. We want to cross multiply those two. Guys, I forget that you have a period for science. In fact, for mathematics, I mean. So I think, guys, you can quickly run and go to the maths class. Ne?
So there's no maths today.
Oh, there's no maths. I see a link in the official group chat, but that's
There
fine. So
is.
we can proceed then. Yeah, no, quickly run, guys. I'll finish this question with those who will be remaining who are not doing maths. I'm not sure who are those. But if there's no one remaining, I'll just finish the recording by myself and make sure that I send it to you. Thank you so much for coming. Please enjoy mathematics. All right, so from this point, we just cross multiply and we say, okay, fine. On the right-hand side, we get 3.6 times 10 to the power 4. And on the left-hand side, we get 6.75 times 10 to the power 5 times R squared. And of course, according to mathematics, we understand that this is a problem, the coefficient of R squared. So we need to divide both sides by this coefficient. And if we now go to the calculator and say 3.6 times 10 to the power 4 divided by 6.75 and so forth. Well, the simplest we can get is 4 over 75, because if we write it as a decimal, it has many threes. So we can just write it like that. And then after we introduce the square root on both sides, your calculator is going to give you something like 2.309 times 10 to the negative 1, if it is still in scientific notation. You can correct that by saying shift and then mode and returning it to normal, which is option number 8, okay? So this means your R is just going to be 0.23 meters. And that is the distance between these two spheres, and your happiness should be complete.